So string breaking then, quenched approximation on the lattice is where you don't have dynamical quarks, but in real life, of course, even in the perturbative cascade, that can happen, that you have a gluon breaking to QQ bar. But the perturbative kernel, the gluon splitting kernel that you may have seen in your perturbative lectures, gluon to QQ bar, we can't use that because this is not perturbative physics. So we can't just calculate it from a Feynman vertex. The model that we use is called the Schwinger mechanism. It's an old effect calculated in the 50s. He did it in QED. And so it's just you have an extremely strong electric field. Imagine that you have that. And you can crank the field strength up so much that you can actually start creating E plus E minus pairs in between, your plates or whatever you have. So you have to have an extremely strong force field to do that. People are working on achieving that in experiments now. It still hasn't been done. Julian did the calculation in 51. And so it's sort of a tunneling probability where you have the field has to give enough energy to create an E plus E minus pair. That's sort of fluctuation is fine, but to make them on shell, you have to take an electron positron mass from the field energy and give that to the electron positron pair, along with whatever transverse motion that you give to them as well. So you have this characteristic tunneling factor with which results in a Gaussian suppression in the mass and the PT, the motion transverse to the electric field. And then in Schwinger's calculation, this is the electric field strength down here. I've just already replaced it by the string tension equivalent. So the energy density, how much energy do I have? I've got kappa, 1 GeV per Fermi of string that I have. And I've got to create some masses and some transverse momentum out of that. So that's the analogy that we make. Again, I didn't derive this from the QCD Lagrangian. I'm making an analogy with an effect that appears in QED. There are some papers that have studied the case in QCD and that argue that this is the same thing that happens in QCD, but we're not entirely sure. So this is a modeling aspect where you say, okay, I will make this assumption that the spectra will be Gaussian. And it's very nice because, of course, it factors off the mass dependence from the PT dependence. These are two separate Gaussians. You can just write them as products. So you can have a strangeness probability. The strange mass is higher. And you can have a Gaussian PT broadening. It's a very simple model. So you get Gaussian suppression of that. And then you put a probability density like this, just constant on this entire world sheet that you have. Constant per unit space-time area. A string is completely self-similar. It's a linear potential. If you're somewhere on the string, you have no idea how long it stretches. It's completely local. It's all completely self-similar, longitudinally boost invariant. So on this entire world sheet, you put, at any given moment, it just has a probability to do this time. And then you can calculate the consequences of that. So now we turn to the string fragmentation function. How do we actually parameterize string breaks? So if we consider that the string breaks in this point here, where I've put the little yellow star, it produces then a meson, is what we're saying here, that break results in a meson over here, and then some leftover string that can fragment further. Just randomly, let's say that that's what happens. Then we can talk about how much energy, light cone momentum, does this meson take, and we can parameterize that by a probability distribution. I already mentioned fragmentation functions. This is a particular instance of a fragmentation function in the context of string fragmentation. Now, to constrain that function, I said, well, in principle, we could just let a neural net do whatever it wants, but maybe we know some things that can constrain the functional form. One crucial observation that we make is that you can see that this break here, this is in space-time. In the forward light cone of the break up here, there's no more string. The string has already broken. So I cannot have further string breaks in the forward light cone of a break that has already happened. Breaks can only happen in these regions here, which are space-like separated from this break. So if we generalize that, all string breaks are causally disconnected from each other. They're all at space-like distances from each other, which means we cannot have information transfer between them. They can be entangled, and there can be interesting effects of that because they all started from the same point, right? So they can make some agreements and shake hands on stuff here when they're produced, but they cannot communicate directly at later times. So there can be entanglement, but no direct information exchange between them. So that means that there's no physical order to the string breaks. Right? We can think of the string as sitting there and string breaks happening in time, but if they're if they're at spatial separations from each other, then we know that we can consider them in any order. The time ordering is not a Lorentz invariant quantity. And we exploit that to say that actually we will fragment the string from outside in. So we will take a string and pop hadrons off its ends and then sort of iteratively make it smaller. That allows us to split off one on-shell hadron at a time and then impose the hadron mass spectrum in a very nice way. That is actually the inverse to the time ordering, but we don't care because we can consider them in any order we want. And also, it shouldn't matter whether I fragment it from the right or from the left. No matter which way I go, I should get the same result. And that imposes a symmetry on the fragmentation function, that the order in which, if I come from the right to the left or left to the right, shouldn't matter. So this fragmentation function is constrained to have a specific form that obeys this left-right symmetry. And I won't go through the steps of deriving it, but that is how you arrive at this Lund symmetric fragmentation function, that if you do anything with non-perturbative tuning or fits with Pythia, then you will see these A and B parameters, which are then the free parameters that have to be constrained to data. But the functional form is constrained by left-right symmetry and causality. So that's quite nice. Still quite a predictive model in momentum space, but it's not very predictive in terms of the flavors that we get out. Okay, so now you then do that many times. You start with this quark, this fast parton that comes out of the shower. There's some infrared cutoff where you stop your shower. You form that you map to strings, and you have the first parton that comes out. Then you create a quark-antiquark pair using this Gaussian suppression of mass and PT. You form a hadron out of the antiquark that you get plus the quark. You add up their momenta and the fraction z that you picked from the fragmentation function with your A and B parameters, and you get what's called the first rank hadron. Then you have a leftover, in this case, down quark, which goes here. You generate another break, and so on and so forth. And that's how you fragment the whole system. So you see how this still looks quite similar to that algorithm we had on one of the first slides. It's just now in a full-fledged string fragmentation context, Lorentz invariant, and we've used causality and a bunch. So it's much more physical, but it's still essentially the same algorithmic process that's happening. On average, then we expect the light cone momentum or the energy of the nth rank hadron. So you see how these z's are sort of multiplying up here to scale like sort of the average z to the power n. We take a fraction z each time, times whatever the starting energy was. So for a large system, we then have all these breakups where quarks and antiquarks meet and they become hadrons. So you see I have two breaks here, and that they then start building little yo-yos. So that's essentially what happens, that we build little yo-yos that then go off with their little string pieces inside them. And you can also see that hadronization, the creation of a hadron, is a slightly non-local process here in the string fragmentation. So you can ask, at what space-time point, or at what time, sometimes people ask, at what time did a hadron form? Well, this hadron formed from these two string breaks, which happened at two different points in space-time that was spatially disconnected. So hadron formation in this model is a somewhat non-local process. It's a little piece of string that becomes a hadron. Okay, so one of the predictions that you get out of this is that you get, the main prediction is that you get a constant rapidity density of hadrons along the string. So we are doing these z fractions down. And if you look at what rapidity, here's just the definition. And you look at the limit where the energy is very large compared to the transverse momentum and the mass, then you see that rapidity is something like the log over energy over mass. From the previous slide, I said we expect the energy of the nth rank hadron to scale like this. So we get that the rapidity of the nth hadron that we are making is sort of n times log z plus a constant thing that's just how long is our rapidity plateau. So if we take the difference between two hadrons anywhere along the string, we see that that is just the log of the average z. So that is independent of n. So this is just a constant difference always. So we expect that the density of hadrons in rapidity is constant. We expect a plateau, a flat distribution of hadrons in rapidity coming from the fragmentation of a string, where that's independent of n and E0. That's also called light cone scaling because it's actually the light cone momentum that we take. And that's exactly what's observed in practice. So here's a distribution from LEP, where you see the sort of rapidity axis here. And you see that there's a more or less flat distribution here. There's a slight incline on it, and there's a good reason for that. And then it drops down when you run out of energy. So you've only got a certain amount of energy in a quark. And at LEP, this was LEP 2, so you had about 100 GeV per quark. And then you can only generate hadrons up to some rapidity, and then you run out of energy. You can't create any higher rapidity hadrons than that. So what you expect changes with the quark energy is not the density of hadrons, right? That was independent of E0, but it's the size of the rapidity plateau. So a very fast quark can generate a long rapidity spectrum, but the density in the middle, so you created a long string, but in the middle, a string just sits there and is completely local and has no idea how much energy the endpoint has. You're just creating this constant density of hadrons. So that's, I think, something useful to keep in mind when you think about particle production from these things. And of course, the rapidity axis here is not the one that we usually think about in hadron collisions, which is the beam axis. The rapidity here is really the rapidity axis, the longitudinal axis of the string in this context, right? So if you have a quark going out that way, then it'll stretch a string along its own motion. And then at some point, it'll be connected to some other quark or whatever. So it's really in the center of mass of this pattern and its color partner. So it's a generalized notion of rapidity. It's along the string axis. And of course, beam remnant fragmentation does take place along the beam remnant axis. So there is a rapidity plateau at the LHC along the beam axis, but jets will have rapidity axes that go out along the jets, not along the beam necessarily. So if I change the energy, this is what you can see from LEP 1, 91 GeV to 206 GeV, the rapidity spectrum gets, well, it gets a little higher, and that's important. That's what you've learned about in the previous lectures, that yes, if I have a higher energy quark, I will also emit more bremsstrahlung. This is not just two quarks that will stretch a longitudinal string between them. There will also be bremsstrahlung. So this additional activity that you get at zero rapidities is because of gluon radiation that increases with the energy of the quark. So we do expect that to happen, but the rapidity spectrum here also gets a bit longer. If we just take the ratio, we would expect that to be 0.8 units in rapidity. It's actually only 0.5, and that's because the quark has to lose a bit more energy to bremsstrahlung before it hadronizes. So everything tallies here. It's sort of the correct intuitive picture that we can build up. Okay, I mentioned gluon kinks. And so we do get more hadrons in gluon jets. This is the number of tracks in a gluon jet than we do in quark jets. And the models sort of predict that qualitative trend. But interestingly, there are differences between Herwig and Pythia that goes into the details of separating quark and gluon jets. That's a very active field right now, where everybody gets this sort of notion that the gluon has more color charge, more strings in a string model attached to it, and also in the cluster model, they fragment it to more partons, more hadrons. But the details of it, if you really want high precision quark-gluon jet discrimination, are subtle. And so now this is one of the challenges, trying to really, okay, after we have this qualitative agreement with the physics, what's the next step in order to really do better than that? So the cluster model is an alternative where you take the gluons at the end of the cascade and you force them to break into QQ bar pairs. Instead of strings, I had my strings here, my string with kinks, where the gluons were kinks. In the cluster model, I take each of the gluons and I force it to break into QQ bar pairs. And so I get little QQ bar, so-called clusters instead of strings. So it's a way of basically preceding some effective string breaks right where at the point where the gluons are. And you get a universal spectrum, and you can fit this model to data as well. It's maybe a bit more crude, I think. Don't think its authors would disagree with that. And there are some things that you have to do when these clusters can come out accidentally with very large masses. And so we would still see them as a longitudinal string, but whereas in the cluster model, you would take each cluster and naively decay it isotropically. But there is actually a longitudinal axis when the mass, or there should physically be a longitudinal axis when the mass starts to become large. So basically the people who do cluster fragmentation, Hilary and Sherpa, for large mass clusters, they have to supply a sort of an axis. They split these large clusters into smaller ones along an axis. So they have to start sort of doing a bit string-like stuff for large clusters. Whereas Pythia, if we have very small mass strings, right? I talked about the string model in the limit that it was infinitely long and infinitely narrow. So I was in a very large invariant mass limit. When we have very small strings that are start to be sort of as fat as they are long, that is not a good approximation anymore. So the string model breaks down for small masses. And guess how we model those? As clusters. So, no matter where you start from, there's kind of you have to, in the end, get sort of similar physics out. So I was going to illustrate the fragmentation function. There are some A and B parameters. I can post the slides and you can have a look at them. You vary them, the fragmentation function changes between having more hadrons with high X fractions, but not so many, because if each of them takes a lot, then you don't get as many, or having more hadrons with small momentum fractions, then you can produce more. So does your string fragment into 2 hard pions, or does it fragment into 20 softer ones? That's what this function describes, these A and B parameters. And no surprise, you can fit that to data. So I won't go through that. Tuning, I think I'll describe tomorrow, but we've talked about the longitudinal part of the fragmentation function and this PT broadening. Again, if I give the quarks more PT in each string break, then I'm using energy to do that, and I won't be able to make as many hadrons. So do I make fewer harder hadrons or more softer hadrons and so forth? And then I have to say how much strangeness suppression there is, what are the ratios between spin 1 and spin 0 hadrons that I'm making, and so forth. So those are the parameters that you would play with in a tuning context for non-perturbative models. I think these are just illustrations of how this looks when you actually compare it to data. I don't think that is so important. So in the next lecture, we'll discuss, these were the basics. I hope they made some sense. We'll try and embed this in an LHC collision and see how we go.